So, in this lesson we are going to learn about ray tracing for lenses and lens system. This technique we used in mirrors and imaging through mirrors. For lens also, let us see how to develop it. So, we use certain concepts for ray tracing. Suppose this is a lens, then all the rays parallel to the principal axis meets at the focus. So, they pass like this. So, this is the focal point. Another point we use is that if the rays are parallel but not parallel to the axis, so if this is the focus, then they will meet somewhere on the focal plane. These two are very, very essential ideas. Next, one more point, if something is placed at the focus, then any ray passing through it will come out parallel to it. And if this is at the focal plane, if this is at the focal plane, you see this, any ray here will pass parallel, come out parallel from deviating from the lens. These are the essential points we take care when we draw the ray diagram. And the most important point is that in any lens there is a point called optical center. So, any ray incident on this optical center goes undeviated. So, till now we are always using this concept of optical center as the center, as a point from where if a ray passes it goes undeviated, but we never tried to see where is that point. Is the point is here or anywhere? Where is that point? Is it the center of the lens or where? So, let us first see what is this optical center point, what is this point as the property of the lens, and then we will go through this different ray tracing exercises. Okay. So, now let us see the optical center of a thin lens. So, here this is a convex lens and this is the optic axis of the convex lens. Suppose this is R1, radius of curvature. Suppose I call this point as O1 and this point as O2, and this is R1. So, its center of curvature is here, that is C1, and this surface has its center of curvature at C2, suppose. Now, draw a point from here. Let us draw a line which meets at this point. So, in any direction, this is an arbitrary, it is not a ray, a line we have drawn on A2. This is A2. This is second surface A2. Now, from this, let us draw a line parallel to this line from C1. So, this line will be parallel. So, it is A1. So, let us write it. So, draw a line C2 A2 from C2 onto the surface SO2M. So, this is an arbitrary line. Draw a line C1 A1 parallel to C2 A2 from C1, which meets the first refracting surface S01M at A1. So, this meets at A1. Now, you see we join A1 and A2. Let us join A1 and A2. A1 and A2. So, A1 and A2 meets this optic axis at the point O. Let us suppose. So, this first surface, that is A1 C1, has a R1 as the radius of curvature, and the second surface C2 A2 has R2 as the radius of curvature. Now, you see this line is normal, this line is normal to this surface. So, the tangent plane here, you see this is the tangent plane, this will be normal to this line. So, the tangent plane is here. For A2, the tangent plane is here. This line is on this surface. So, this point is from center of curvature. So, on the tangent plane it is 90. Now, these normals on the tangent planes are parallel. So, the tangent plane, let us just, I am showing it. This is the tangent plane and this is the tangent plane. This is the tangent planes. Now, you see these two tangent planes are parallel. So, you see if I have a parallel media like this, and you see this is A2 and this is A1, then suppose this ray here coming like this. So, the ray will come out like this. So, these two rays will be parallel because these two planes are parallel. So, the medium here and here is same. So, now let us remove these lines so that our diagram will be somewhat easier. This is A2 and this is A1. So, this is A2 and this is A1. So, thus since the tangent planes at A1 and A2 are parallel. Why they are parallel? Because their normals are parallel. So, tangent planes must be parallel. So, the ray, suppose this ray is coming like this and it goes like this. So, the ray incident at A1 in the diagram and the ray which emerges at A2 are also parallel. Thus, you see these two rays emerge parallel to each other when they pass through this point O, or when they pass through A1 and A2. Thus the ray goes undeviated by the lens system. Very important point. So, for this ray there is no deviation. Now, my point is to calculate the point O with respect to the lens. Very important point. Please take down. Now, consider triangle C2A2O and triangle C1A1O. So, you see here in these triangles, these are parallel lines. So, this angle is equal to this angle becomes equal to this, alternate angles. This and this angle is equal because opposite vertical angle. So, you see these two triangles C2A2O will become similar to triangle C1A1O. So, these two triangles are similar, equiangular. So, if these two triangles are equiangular, then we will write C2A2 by C1A1 by equal to C2O C2O by OC1 C1O is equal to OA2 by OA1. This is the proportionality theorem when two triangles are similar. Now you see, we will concentrate on this part, C2A2 by C1A1, C2A2 by C1A1, C2A2 is R2 by C1A1, C1A1 is R1 is equal to C2A2 C2O. Now this is it's equal to this. Now you see, we can also subtract these two, that is C2A2 minus C2O by C1A1 minus C1O. So this ratio is equal to the difference or even the sum of the individual terms by ratio and proportion theorems. So R2 by R1 equal to C2A2, from C2 to A2, you see C2A2 can be also written as C2O2. So C2O2 minus C2O by C1A1, C1A1 is nothing but O1 C1, C1O1 minus C1O. C2O2, you see C2O2 minus C2O, C2O is equal to OO2, OO2. C1O1, C1O1 is this quantity minus C1O, C1O is O1O, that is OO1. So we got R2 by R1 is equal to OO2 by OO1. If R1 and R2 are same, then OO1 and OO2 is same. That is, this is symmetrically placed. But if R1 and R2 are different, this O is not in between this center of the lens. So the center of the lens, geometrical center of the lens is not always the optical center, first point. So optical center is a point O where this ratio by this ratio is given by R2 by R1. So R2 by R1 or R1 by R2 is given by this term. This is the location of the geometrical location of the optical center. So the ray here inside the lens, it passes through the optical center. It may be that this lens, this ray is not actually aimed at O, but when it is thin lens, so this distance is, the displacement is negligibly small. So if we aim at the optical center, then the ray after refraction will go undeviated. Now you see here, suppose we had a lens like this, and at this place suppose a ray is there, suppose a ray is incident like this here. Then what happens? This ray goes like this and then it comes like this. So you see here, this time the ray does not deviate, but this time the optical center is here, optical center is outside. So in such type of problems, in such type of lenses, the optical center may not be geometrically inside it, and the ray inside the lens may not physically passes through the optical center. It is virtually passing. It seems that it is aiming at optical center, but actually it goes like this. So it is not necessary that the first of all optical center of the lens system will be lie inside the physical boundary of the lens, and second point, the ray should physically pass through the optical center. So for this type of lenses, the ray seems to be inside the lens, seems to be falling on the optical center, but actually it comes out from here only. For this type of systems, it will be inside, but for this type of lenses, it may be lying outside the this. So, this is the property of optical center, that any ray aimed at the optical center passes undeviated from it. So now let us take up some examples on ray tracing. Example 1. In this, I have been given a optical axis and this is a converging lens. This is a converging lens and it focus of this lens is here. This is a ray and we have to construct, we have to trace this refracted ray. After refracting from this lens, how this ray will go, that we have to trace out. So we have to trace the refracted ray from the converging lens. So what we do, this is the optical center. So what we have to do, we draw a line parallel to this from the optical center. This line is going to pass undeviated. So my first property is draw a line. Suppose this is object and this is A. So draw a line, first point, draw a ray parallel to OA through the optical center. Next, this is the focus. So this is the focal plane. So next, this is the focal plane and so determine the point B. Determine the point B at which this line and this focal plane meets. That means this ray, these two rays must meet at the focal plane. Next property will be used. That means since all the parallel rays not parallel to the principal axis has to meet on the focal plane and this ray has to go undeviated, that means my refracted ray must pass through B. So join A and B and so this is the ray. So thus we have traced the refracted ray. Next we will see for convex, that for concave lens. This is convex lens. Now let us take an example 2. Here this is the optic axis given and this is your diverging lens, concave lens. This is the symbol we will use for diverging lens and it is given that the focus is here. We have a ray going like this. We have to trace out the ray after this lens. The ray refracted from the lens, how that will go into that medium, that we have to trace. This is our problem. We have to geometrically trace the refracted ray. So as in the previous problem, you take the optical center and draw this to this line, a ray parallel to this. So you see this ray and this is parallel. We know that if any ray is going in this direction, this will pass undeviated. This will pass undeviated. So two rays parallel but not parallel to the principal axis from this lens will have to meet at the focal plane and you see this is the focus. So you see join these two and determine the focal plane and so this, since this ray has to go undeviated, so they will meet here only on this is the focal plane. So this ray, if I produce this, will go like this. So what we do, we draw a line parallel to this ray, incident ray from the optical center, and then we see where they meet at the focal plane, and then we join these 2 points. So you see this ray and this ray, suppose they meet at the focal plane. So this is my refracted ray. This is how to construct this. Let us take one more example. Now let us take another example similar to this, but suppose this is my converging lens. This time it is given that a ray, this ray after refraction goes like this. Where is the focus? The focal length, the focus is not mentioned. We have been given these 2 lines, that this ray after refraction from the lens, converging lens. So this is my objective, then it will be its image. Now we have to draw, suppose I have another ray this, then how this ray is going to refract. So how to this we have to refract, how we have to construct geometrically how this ray is going to refract from this lens. What we have to do is, first we have to determine where is the focus, focal plane. So what we do, from this optical center I draw a line parallel to this. So this line is parallel to this. So you know that since this point line is passing through the optical center, it goes undeviated. That means this is the focal plane. So if I draw from this perpendicular to here, then I got focus. So thus I have determined the focal plane. So first point is to determine the focal plane. Focal plane. The whole diagram should be focused. So once I determine the focal plane, then I wish to know how this ray is going to refract. So again, with a line passing through optical center, and you see parallel to this will be drawn. You see this line will again pass through, this ray will again pass undeviated, and this must meet at the focal plane. And once I have determined the focal plane, I have to join these 2 points. So this is the way in which this refracted ray has to be constructed. Now let us take another example, 4th example. Here we have been given the optic axis, and this is my lens position given. This is the lens position given. This is the place where an image has to be formed. This is the image is there. It is given, and suppose this point is called O, the optical center is given. It is also given, suppose it is given in geometrically, this distance is 10 centimeter. Suppose it is given OI is equal to 10 centimeter and OF is equal to 6 centimeter. OF means the focus. So you see, we have to find out where is the point object for which this lens system makes the image at I. We have to find out the position of object for which this lens system makes an image at I. This OI is suppose 6 centimeter. Now suppose focus is this side. Again I will have 2 cases, when the focus of this lens is this side and when it is this side. So suppose what we do, we take an arbitrary point here and join these two. Let us join these two. Take an arbitrary point and join these two. That means this is an arbitrary ray. And then from the optical center, let us draw a line parallel to this. So the parallel to it, it will be like this. So this is the optical center and the ray parallel to this is like this. Now suppose this OF is 6 centimeter, this is 6, this is 10. So suppose this is F. So now when we have drawn from the optical center a line parallel to this, then this is the OF 6 centimeter, we can draw from both sides this and this is equal to 6 centimeter. Now what we do, we draw a perpendicular here. So this is the focal plane also and this is a focal plane also. So draw this side. So now we join these 2 points. Let us join these 2 points. So when I join these 2 points, I get this source. So now you see here, this is the source when this I is virtual. That means if I keep an object here and this is the converging lens, so that the object is between the focus and the pole, then its image is formed here. So for this case, for suppose I say S1, so S1 is here real object for which I is virtual. So this is the image formed when the source is at S1 and this image will be a virtual image. Now when you see this line meets here, if I join these 2 points, when I join these 2 points, they meet somewhere here and this will be called S2. So for the object at S2, suppose we have an object at S2, the image I is real. That means I is the image for this lens system. This is possible for 2 positions of sources. So if I keep source at S2, I will get a real image at I, but for this same lens. But if I put a source here, then I will get a virtual image at I. So by this ray tracing, we have determined these 2 positions. This is a very important problem. So now let us take one more example of a converging lens. This is S1 is a point source whose image is formed at I1 by this lens system. We have to find out if S2 is here, somewhere here arbitrary, and we have to determine where is the image of S2 formed. So what we do, we take an arbitrary ray like this. This is a arbitrary, in any direction I have taken a ray. And then parallel to this, let us draw from the optical center a ray. So this ray goes undeviated and this ray goes undeviated, and now you see this ray and this ray will meet to form the image. So join these 2 points. So if I join these 2 points, then this ray goes like this. So you see here, this ray, these 2 rays, when this ray is going undeviated and when I join these 2 points, So this becomes the focal plane. This ray bends in such a way that this becomes the virtual image. So now I know that this ray has to go like this because this is the image, so it will bend like this. And this ray goes undeviated, and this ray after refraction must pass through I1. So that means this point lies on the focal plane. So this is the focus determined. So because I know that I1 is the image of S1, so I have determined the focal plane. So now focal plane is determined. Now what I have to calculate? Now suppose the source is S2. There is a point object at S2 where its image will be formed. So again what we will do? So we will join these 2 points, or we will draw a line parallel to this. Let us draw a line parallel to this from S2. So this line will be something like this. Now this line goes undeviated, and this ray has to meet at the focal plane. So again I have to join these 2 points. So we have to join these 2 points. Suppose this point is somewhere here. So I have to join these 2 points, and they will meet somewhere on this line. That will be the I2. So we can draw, let us draw a somewhat like this parallel. So they are going to meet somewhere here they will meet. So that image will be I2. Now let us take another example. This is my convex lens, converging lens, and very near to this we have a square ABCD such that the middle point of DC is on the focus. So how the image of this square will be formed? The image of this square. So what we do? We will join these 2 points. Suppose any ray from A goes like this, and if it passes through this lens system, then it will go parallel to it. So this ray is going to be parallel to this ray. And suppose a ray is parallel to this. If I draw, then this focus is here. It will pass through the focus. This is the focus, and they are going to meet. So the image of A is here at A dash. What about this D? This ray is going, so if I draw a perpendicular here, then this is A dash and D dash. So A dash, D dash, this line will be formed here, and this ray goes like this. So we will see later on about the whole space. Now think about a ray here, this ray, this point BC, this line BC is lying this side. This is between pole and focus. So you will have an image here. So this ray, after this is a straight line. So we have to draw it carefully somewhat. So, and if I join this B and F, so any ray passing through this focus goes like this. So you see here, this is B dash, and this is B dash, and this is C dash. And you see, if I am very near to here F, but this side my image goes this way, and if I am at this place my image goes this place. So you just divide this, and you see this part will have an image like this shaded one. This is A dash, D dash, and this B set is this. So this part will have image plane like this. So the image will be this trapezium extending to infinity, and this half, this I am not shading, will start from B dash C dash and then you see shaded portion. So this portion, unshaded portion of the square assumes the trapezium to infinity, and this half assumes that trapezium to infinity. So this whole square, this part will be lying this side in the form of trapezium with this B as B dash and here C at C dash. So B dash, this up to infinity will be the image of this point, this part, and this part will have an image this side to up to infinity. This is how we have traced the image of this square.